For the do now, there's just one question. I just put one question in for the do now because I want to be able to get through. I didn't even write anything on the board. I want to be able to get through some of the examples for buffers and be able to have you guys have hopefully a little bit of time to practice. So for the do now, it says calculate the pH of a solution containing 0.75 molar lactic acid and 0.25 molar sodium lactate. So if we think about what we did last week, we labeled everything. So lactic acid is a weak acid. Lactic acid is not one of the 7 strong acids, so it's weak. And then sodium lactate. So typically when something starts with sodium, it's a salt, with the exception of sodium hydroxide, that's base. So when it starts with sodium or potassium, that's a salt. When it has potassium, nitrate, ammonium, or sodium in it, it's a strong electrolyte. So it's a salt that completely breaks apart. Once we label everything, what we did next is we wrote what was weak at equilibrium. So I'm going to use Appendix D. Lactic acid is actually HC3H5O3. Lactic acid is HC3H5O3. Could you just do HA for lactic acid? Yes. The HA just represents some weak acid. So here's lactic acid. Because it's weak, it exists at equilibrium with its ions. So lactic acid exists at equilibrium with its ions. Because we're doing a calculation of something that is weak, we will use an ice table. And so we have 0.75 molar lactic acid. But in the container, we also have sodium lactate. Now, sodium is always a spectator ion, so I'm just going to ignore sodium. So really, we have lactic acid and the lactate ion in the beaker. This is the lactate ion. So initially in the beaker, we have the acid and its conjugate base. So we have 2 initial amounts. The goal is to find the pH. Remember, to find the pH, we need H plus at equilibrium, or H3O plus at equilibrium. Now, because I don't have any other information, I'll go ahead and use X's. And using Appendix D, the Ka value for lactic acid is 1.4 times 10 to the negative 4th. Again, the Ka value comes out of Appendix D. If this were a test or a quiz, you would be given the Ka values. You'd be given the values that you need, or you'd be given values that would allow you to find other variables. So my Ka expression, the reason this is Ka, it's an acid because it produces H plus. So that means if it's Ka, we should see H plus in the expression. And then we can fill all of our equilibrium values in. So Ka is 1.4 times 10 to the negative 4th. X times 0.25 plus X over 0.75 minus X. And then what we can do to help is we can assume X is small. By assuming X is small, we can ignore the minus X and the plus X. And we can solve. So I'm going to multiply 0.75 over and divide by 0.25. I get X to be 4.2 times 10 to the negative 4th. 4.2 times 10 to the negative fourth. That's x. Now if we think about it, x is H plus. This is the concentration of H plus at equilibrium, which means to find the pH, we just take the negative log. Negative log of this value is 3.38. So the pH of this solution is 3.38. We had a weak acid with a little bit of its conjugate base. So we had more weak acid than its conjugate base, which is why we see more of an acidic pH. So this is a common ion problem, but this is also a buffer. A buffer just gives common ion problems kind of a definition. We'll talk more about buffers on the next slide, but when you have a weak acid or weak base and its conjugate, so in this case we have a weak acid and its conjugate base, that's a buffer. Now notice how we solved the buffer using the common ion. You can do that as well. There are different ways that you can solve a buffer problem, whether you want to use common ion or you want to use the buffer equation that we look at today. Any questions on the do now before we look at buffers? Yes. I think he's a little weird.
Oh, you're just like a little thing.
You want mustaches or lips?
Hey, we're gonna do it. We are going to try it.
You really do it one
Okay.
You stand there with a pan. You have to.
I mean,
Yeah, that's why. That's how we All right, so before we get into buffers, just looking at this week. So this week we're going to work through 8.2 and 8.3. 8.2 is buffers. So we're going to spend today and tomorrow looking at buffers, doing some practice with buffers. And then Wednesday, Thursday, Friday, we'll get into titrations. We will continue into titrations next week. That's really kind of the bulk of this chapter, is looking at titrations, because that's going to tie a lot of the things together into one problem. So we'll work through 8.2 and 8.3. Remember, there's mastering, so you'll notice like today, you'll have some time to work on mastering. Wednesday night, there's no video, so you just work on mastering. That's due next Wednesday at 7:30. Remember, next Wednesday is also when the bonus is due. So if you want to do the bonus, that's due next Wednesday as well. So if we look at buffers, so this is from page 4 of the notes. I just copied and pasted a lot of this stuff out of the notes packet to just talk about what exactly is a buffer. The question that I saw the most on video 8.2 was, what is a buffer? Why do we use a buffer? Or what's the importance? A buffer is used to resist pH changes. Tomorrow, assuming that we're here for the full time, I'm going to actually show you how a buffer system works. So I'll do a demonstration on the document camera so that you guys at home can see it as well. But we're going to look at how a buffer actually works. The point of a buffer is to create this system that is composed of a weak acid or weak base and its conjugate. So you always have an acidic component and a basic component of a buffer. And when you add acid or when you add base, the buffer reacts accordingly and keeps the pH from changing very much. We have a buffer system in our blood. So we have carbonic acid, H2CO3, and then its conjugate base is hydrogen carbonate, HCO3 minus. So that keeps our blood at a pH of about 7.4. So if something causes our blood to become more acidic, the buffer works to keep the pH at about 7.4. Something basic is added, right? The other component of the buffer works to keep the pH at 7.4. So the point of a buffer is to resist pH changes. So no matter what gets added, the pH stays as constant as possible. It neutralizes small amounts of acid or base because you have an acidic component and a basic component of the buffer. And I'll actually show you using these particles up here in a second. So this is really important because if you have a reaction or you have a system like our blood, right? We don't want the pH of our blood to change. And so a buffer is really important to keep the pH stable. Buffer solutions have what we call a working pH range and a buffer capacity that tell us how much acid or base can be neutralized. So we can't add, 1,000 milliliters of acid and hope that the buffer keeps the pH the same. The point is that when a little bit of acid or a little bit of base gets added, the pH stays the same. We can do what's called break the buffer. So if you add enough acid, you're going to hit a point where the pH no longer stays constant. The pH is going to drop drastically if you add acid, or it's going to increase drastically if you add base. Now the best buffer down here at the bottom, the best buffer has a high buffer capacity. That means it has high concentrations of the acid-base pair. If it has high concentrations of the acid-base pair, that means that more acid or more base can be added and the buffer continues to work. And again, we'll look at that on the next slide when I use these particles up on the board. So in the video, I talked about 4 ways to make a buffer. Right, this is in your notes. I copied and pasted this directly from the notes. The first, or I should say the third and fourth way on here, we actually looked at on Friday when we looked at the neutralization reactions, and we had an acid and its conjugate base existing at the same time in the container. So you can create a buffer through a neutralization reaction. That's a titration. We'll talk about that more later in the week. Or we can make a buffer by adding a weak acid and its conjugate base. Notice how the conjugate base comes in the form of a salt. You can always ignore Na, so it gives us HCN and Cn minus. Or a weak base and a salt. So that salt has the conjugate acid. Cl minus we can ignore as well. So we have NH3 and NH4 plus. That's also a buffer. It always just needs an acidic component and a basic component. Because if it doesn't have an acidic and a basic component, the buffer's not going to work. So let's look at how a buffer actually works. This is in your notes as well. But if I have a buffer, so I have a buffer that has HF and F minus. So here in our little container, we have HF and F minus. Right, so in the beaker, I have equal amounts of HF and F minus. I have 2 particles of each. The point of a buffer is that when we add either an acid or a base, one part of the buffer is going to react to neutralize whatever is added. So if we look at adding OH minus, if I add an OH minus into this container, part of the buffer will react with OH minus to neutralize it. OH minus is a base, which means the acidic part of the buffer will react with OH minus. HF is the acidic part, right? In this buffer, we have HF, which is a weak acid. F minus is the conjugate base. So if I add OH minus in here, the HF will react to produce H2O and F minus. By this neutralization reaction occurring, the pH isn't going to change very much. Will it change a little bit? Yes, because we have 1 extra F minus. but it's not going to change like it would if we just added a strong base of OH minus. So when you add a base, the acidic part of the buffer reacts to neutralize and produce F minus and H2O. Now what if we went the other way? What if I added a strong acid like HCl? Cl minus is neutral, we ignore that. Well, if I add a strong acid into here, the basic component of the buffer, which is F minus, will react to produce HF. Because HF is a weak acid, the pH does not change as much as if we had H plus from HCl. So the buffer always needs an acidic component and a basic component, a weak acid and a weak base. If you don't have one part of that, you don't have a buffer. All right, so adding a small amount of acid or base will only slightly change the components of the buffer, so that's why we don't see a change in pH. Eventually, and let's look at if I do this. If I add a lot of strong acid, let's say I add 4 molar of HCl. Well, here's part of the base. Right, the basic part will react with the H plus. Here's another F minus that can react with H plus. But now I've broken the buffer. Notice now I don't have any other basic part of the buffer to react, which means now I'm just adding strong acid. The pH is going to drop. So instead of the pH remaining at, say, 4.5, now I'm adding all of this strong acid, we'd see the pH go down to maybe 1 or 2. But as long as we have an acidic component and a basic component, the buffer will work. You do the same thing with OH minus. I could get more OH minus and add enough until we broke the buffer. So making a buffer, right? I kind of showed the buffer here. But how to actually make one, and I'm hoping we can get into the lab, if not this week, maybe even next week, to just look at how to make a buffer. So this is on page 5 of the notes. So you're going to use some concentration, right, anywhere from 0.1 to 1 molar, and you're going to choose an acid that has a Ka near the H plus concentration that we want. Now, if we think about that in a little bit easier terms for us, the pKa should be as close to the pH as we can get it. pKa means you take the negative log of Ka. So the pKa should be as close to the pH as it can. If we want a pH of 5, we need to look for an acid that has a pKa near 5. And then we can change the ratio of acid to base as needed until we can get to that pH. And then a lot of times we're looking at moles, right? So we're not really going to look at grams, we're looking at moles, or we're looking at concentration when it comes to buffers. So now, solving buffer problems. You are only required to calculate the pH of a buffer. So in terms of calculations, you are only required to calculate the pH of a buffer now. I'll show you on the next slide. Even last year, I made them do adding something to a buffer. You don't have to do that anymore, so I said, well, we're just going to take it out. So there are 2 different ways to calculate the pH. I show everyone this first equation because it's on the equation sheet. We do not use this equation, and I'll tell you why. So the first way that you could solve a buffer problem is to use what's called the Henderson-Hasselbalch equation. This is in your textbook. This is on the equation sheet. That's pH equals pKa plus log of the base concentration over the acid concentration. Now here's why I don't use this. I used to, but this equation differs whether you have an acid buffer or a base buffer. So if you have a buffer that is NH3 and NH4+, this equation is going to look different. So instead of having to memorize two different Henderson-Hasselbalch equations, we just use the buffer equation that I gave in the video. So instead of using the Henderson-Hasselbalch equation, again, if you want to use it, fine. We just use what I call the buffer equation. All it is it's a rearranged Ka expression. So this was in the video, right in the box, it said buffer equation that we will use. This is it. H plus concentration equals Ka times the acid concentration over the base concentration. It doesn't matter whether you have an acid buffer, it doesn't matter whether you have a base buffer. We use this every single time. You have to make sure you're using Ka. If they give you Kb, then you better figure out Ka. It's always H plus equals Ka times acid concentration over base concentration, no matter what. Now, this is the part that I decided to take out this year, right? No longer tested. When you add something to a buffer, even as soon as last year, I was making them do this. This is probably the most difficult part of buffer problems, and now we don't have to do it. And that is figuring out what the pH is after something is added. So if you added HCl, what's the pH? If you added NaOH, what's the pH? That is no longer tested. All you have to do is figure out what is the pH of a buffer. And we'll look at some other conceptual questions as well, but we're going to use this buffer equation to figure out what the pH is. And so what we're going to do is we're going to go through and do some examples. So we'll start with example 4. This is on page 17 of the notes. So on page 17, we have example 4. So this says, explain why a mixture of HCl and KCl does not function as a buffer, but a mixture of acetic acid and sodium acetate does. So when we're thinking about a buffer, I always like writing down what a buffer is first. So a buffer must have a weak acid conjugate base or weak base conjugate acid. In order to function as a buffer, we should see a weak acid and its conjugate base or a weak base and its conjugate acid. So we need to look at the components. We always need an acidic portion of the buffer and a basic portion of the buffer. Otherwise, it's not going to neutralize acid and base. So if we look at HCl, what is HCl? Strong acid. KCl is a salt, which is fine, but that means that Cl minus. If HCl is a strong acid, Cl minus is neutral. It's not basic. So that means that if we're thinking about this, we have a strong acid and something that's neutral. That can't be a buffer. Right, so, oh, there's both of them, okay. Now you don't have to necessarily write all of this, but HCl is a strong acid, Cl minus is neutral, right? Negligible base means it's neutral. So this first example, HCl and KCl, does not have a basic part of the buffer. HCl and KCl does not have a basic part of the buffer. So if you add strong acid, let's see if I can get this while you guys are writing this down. So here's Cl minus. And HCl is a strong acid, so it breaks apart completely. if I add more strong acid into here, the whole point of a buffer is that there's a basic component that reacts with the added acid. All this is a solution of HCl. There's no basic part to react with added acid. However, acetic acid and sodium acetate is a weak acid with its conjugate base. So acetic acid is a weak acid. Remember, sodium is always a spectator ion, so we can ignore that. Well, now we have a weak acid conjugate base. That acts as a buffer because if we add in base, we add in OH minus, acetic acid will react to neutralize. If we add in some acid, some H plus, acetate is a weak base because it comes from a weak acid. So acetate, a base, will react with any H plus to neutralize, and the pH will stay fairly constant. So in order to have a buffer, we have to have a weak acid and conjugate base, or a weak base and its conjugate acid. It's kind of just the definition of a buffer. So now if we look at example 5, so this is actually doing math now, right? Calculating. So what is the pH of a buffer? It is 0.12 molar lactic acid and 0.10 molar sodium lactate. Looks fairly similar to the do now. We know it's a buffer. It says pH of a buffer. If it says buffer, write that buffer equation. Concentration of H plus equals Ka times concentration of acid over concentration of base. That's our buffer equation. We just use the concentrations that they give us to plug in. Because remember when we assume X is small, like we did in the do now, we ignore that minus X anyways. So we can use the buffer equation to solve for H plus. And when we find H plus, it's easy to find the pH by taking the negative log. They gave us the Ka here. 1.4 times 10 to the negative fourth. And now for the buffer, you have to figure out what is the acid component and what is the base component. We have lactic acid. There's our weak acid. So 0.12 molar is our acid component. And 0.10 molar sodium lactate. Remember, we can ignore sodium. We have lactic acid. Lactate is the conjugate base. So our molarities cancel out, which is what we want. 0.4 E negative 4. Let's do this really quick. So H plus 1.68 times 10 to the negative fourth molar. And then how do we find pH? Take the negative log of that. Okay, so for example 6, we're going to get into calculations, but also actually look at what is happening with the buffer as well. So a buffer is made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of solution. What is the pH of the buffer? So again, we know it's a buffer because, well, it tells us, which means write out the buffer equation first. So the concentration of H plus is Ka times the concentration of acid over the concentration of base. No matter what the components of the buffer are, this is always the equation that we use. Now, just to help, let me give you the Ka of acetic acid. Ka of acetic acid is 1.8 times 10 to the negative fifth. Now remember the brackets means concentration, so you need to know what is the concentration of each. Concentration is molarity, moles per liter. So go ahead and plug in Ka, plug in your concentration of acid in your base, solve for H+, and then see if you can solve for pH. So because you have equal concentrations of the weak acid and its conjugate base, the H plus concentration actually just equals the Ka. And then we take the negative log, 1.8 times 10 to the negative fifth. pH is 4.74. So since the acid and the base concentrations are equal, right, that results in a ratio of 1. H plus equals Ka, so pH equals 4.74. pH would equal pKa. So then part B, write the balanced net ionic equation for the process that occurs when NaOH is added. So remember that Na is a spectator. So I'm actually going to focus on what happens when OH minus is added. The whole point of a buffer is that it has an acidic component and a basic component. So when OH minus is added, OH is a base. So the acidic part of the buffer is going to work to neutralize this added base. The acidic part of the buffer is HC2H3O2. So let's do this. H C2H3O2. Yeah, so since it wants net ionic equation, I'm going to ignore Na plus. If it wanted the molecular equation, we could show the whole thing. But since it wants net ionic, I'm just going to show OH minus. So since it just wants net ionic, we're going to ignore the Na plus because it's always a spectator. So when we add OH minus in here, the acid is going to work to neutralize. So the acid is going to donate the proton to OH minus. And that will produce H2O. And that leaves us with C2H3O2 minus. Since this neutralized, right, water is neutral, pure water is neutral, and that leaves us with the conjugate base. So it's not going to change the pH very much. And so that's actually how a buffer will work. The acidic part will neutralize with added base to produce water and the conjugate base. Then part C, what is the pKa of the weak acid? All right, so remember that pKa, this lowercase p, means we're taking the negative log. So pKa means we're taking the negative log of Ka. So pKa means we're taking the negative log of Ka. So the weak acid, that's the acetic acid. This all goes together. Ka was 1.8 times 10 to the negative fifth. The negative log of 1.8 times 10 to the negative fifth is 4.74. It says, how does the pH compare to the pKa? We calculated the pH in part A. How does the pH compare to the pKa in part C? They're equal. The importance of the pH and the pKa is that we can actually tell what we have more of in a buffer by comparing the pH to the pKa. And so on the next slide, this is actually out of your notes, right? This is back on page 5 of your notes. If it helps you to just write this information down at the bottom within this example, just if that's where it's going to be easier for you to find it, that's okay. College Board loves asking questions like this now. Every year we've seen a question like this where they ask about what you have more of based on the pH and the pKa. So we can figure out the relative concentrations. HA just means weak acid, A- just means conjugate base. Could represent anything. In the last example, this would have been HC2H3O2, C2H3O2 minus. But the relative concentrations of the weak acid and weak base can be determined by comparing the pH to the pKa. So in the middle, in the last example, we said that pH equals the pKa. When the pH equals the pKa, there are equal amounts of the acid and the base in the buffer. So if you actually look at the last example, there were equal amounts of acetic acid and sodium acetate. Because there were equal amounts, they canceled out, and that gave us pH equals pKa. If pH is less than pKa, so think about it, a lower pH means more acid. So if pH is less than pKa, the acid form of the buffer is present in a higher concentration. pH is lower, more acidic. If it's the other way, if pH is higher, think about what that means. Higher pH, more basic. So if pH is greater than pKa, the base form is present in higher concentration. So if we think about it, let's say that we had something like this, right? This was our buffer. We still have an acidic part and basic part, but we have more base compared to weak acid. So we would expect the pH to be greater than the pKa. In the example that we just looked at, it was this. There were equal amounts of the weak acid and the weak base. When there are equal amounts, pH equals pKa. If it were the other way, right, like this, you have more weak acid than weak base, you would expect the pH to be a little bit less than pKa. So these are always questions that they like asking, comparing pH to pKa. So example 7. A buffer is prepared by adding 20 grams of acetic acid and 20 grams of sodium acetate to enough water to form 2 liters of solution. Determine the pH of the buffer. So again, determine the pH. I'm going to write the buffer equation because it says pH of the buffer. So the buffer equation is H plus equals Ka times concentration of acid over concentration of base. In order to calculate the pH, we need to figure out what's the concentration of the acid, what's the concentration of the base. Again, we're using acetic acid. Acetic acid is one that we use often. It's a very common weak acid, weak base buffer. So 20 grams of acetic acid. I cannot plug grams in. Brackets means molarity. So I need to figure out what's the molarity. If I have 20 grams of acetic acid in 2 liters of solution and 20 grams of sodium acetate in 2 liters of solution. So let's figure out acetic acid. HC2H3O2. 20 grams. I'll give you the molar mass. 16.052 grams. It's 1 mole. That's going to give me my number of moles of acetic acid. If I divide by 2 liters of solution, that gives me molarity. then we can do the same thing for sodium acetate. 3 grams. 82.034 grams. Mole. Gives us our number of moles over 2 liters. So take a minute and solve. Take just a minute, solve for your moles, divide by 2 liters to find grams. So there are the concentrations that I got. 0.167 molar for acetic acid, 0.122 molar of sodium acetate. Now to plug in, you need to know which part's the acid, which part's the base. Here it even says acetic acid, that's a weak acid. Sodium acetate, well, the acetate ion is the conjugate base. The Ka we looked at in Appendix D before, that was 1.8 times 10 to the negative fifth. Remember, you have Appendix D, so if you're working on mastering and it tells you to use Appendix D, that means you need to find the Ka value from there. So 0.167 divided by 0.122. The importance of using this buffer equation is that it has to be in molarity. So H plus 2.46 times 10 to the negative fifth molar. To find pH, we can take the negative log of that. .61. Now, could you solve this as a common ion problem instead? Yes, we could. We still get the same thing. But because it says it's a buffer, you can just use the buffer equation. Part B, write the complete ionic equation. So complete means we have to show everything. Complete ionic equation for the reaction that occurs when a few drops of hydrochloric acid are added to the buffer. So I have HCl. So I'm going to write the molecular equation first. Molecular meaning everything is still together. If I add HCl, that is an acid. That means that to keep the pH relatively constant, the basic part of the buffer needs to neutralize the acid. So if I'm adding acid into this container, the basic part of the buffer needs to react. Well, if I look at what I have in this container, I have acetic acid and acetate. The acetate is the basic part of the buffer. So the sodium acetate, the sodium acetate is what will actually react. And the reason that I have sodium acetate together is because it wants the complete ionic equation. So then if we look at what this produces, the double replacement reaction. Na and H plus will switch. We get NaCl. and HC2H3O2. So we have to think, okay, NaCl is a salt. Does it contain potassium nitrate, ammonium, or sodium? Yes. It's aqueous. HC2H3O2, that's acetic acid. Is acetic acid one of the 7 strong acids? No. So when we think about breaking things apart, HCl is a strong acid, which means it actually exists like this. HCl is going to break apart into H plus Cl minus. It's a strong acid. Sodium acetate is going to break apart. It is a salt. It's ionic. It contains potassium, nitrate, ammonium, or sodium. So Na plus C2H3O2 minus. NaCl is going to break apart because it's a soluble ionic salt. Right? A soluble salt, an ionic substance that contains potassium, nitrate, ammonium, or sodium. I put an X under acetic acid. Only strong acids, strong bases, and soluble salts break apart. Here's our complete ionic equation. Complete ionic means you don't cancel out spectators. Means you don't cancel out spectators. So that means that we have this in solution, right? This is what our beaker looks like after. There are NAs, I would need to pull out. There you go. That's what would happen after. Then finally part C, so let's reset this. Part C, write the complete ionic equation for the reaction that occurs when a few drops of sodium hydroxide are added. So sodium hydroxide is being added, so let's write NaOH. That's a base. Is NaOH a strong base? Yes, it's part of the B on the periodic table. So I'm just going to put an arrow down to tell me that that's going to break apart. If we are adding a strong base into the container, the acidic component of the buffer will work to neutralize. So when this goes into the container, right, this will break apart because it's a strong base. The acidic component of the buffer is going to neutralize, meaning it creates water. So the acidic component of the buffer is acetic acid. Acetic acid is a weak acid. Notice how I brought acetic acid up to the OH minus as a molecule. So then if we look at this neutralization reaction, it's double replacement. We get HOH, which is H2O. That's what happens here. And then we get NaC2H3O2. That's a soluble salt. It has sodium in it. That means it's going to break apart. Notice how it's already broken apart in here. So if we break everything up that can be broken apart, we have Na plus OH minus. Keep acetic acid together. It's a weak acid. Notice in solution here, we have acetic acid together when it can be. H2O doesn't break apart because it's a liquid. Sodium acetate breaks apart because it's a soluble salt. So here is our complete ionic equation. So the next example 8 we'll get to tomorrow. Just for something for tomorrow. So I had said that there's no video for tonight, but just kind of looking ahead. If you work on mastering, numbers 1 through 4 are the common ion questions. 5 through 13 are the buffer questions. You can start looking at that. I did put something on Classroom. There are 4 practice questions, right? What we used to do is we used to just split up into small groups and work through them in class, but since we had the 2-hour delay, we don't have the time. And so I put it on Classroom. What I want you to do is look at those 4 questions. I just have them on Google Slides, so just work through them on like a separate piece of paper. It's very similar, like calculate the pH of a buffer. Which buffer might you pick? Just try them. Tomorrow at the beginning of class, we'll go through, we'll look at the answers, you can ask questions, things like that. But that's it in terms of for tomorrow, right? No video, just work through those 4 questions. If you want to start working on mastering, you can. Then we'll do example 8 and the practice with the buffer. So if you didn't get that practice packet last week, it's still in the top tray. We're going to be working through that tomorrow.